Hello Internet, my name is Quinn and this is Blondihacks. We're wrapping up the robot end effector build today for Dragonfly Engineering. We've got to make a couple of little extension parts and we're going to get to see how these things get used on the robots. So let's go. Here's what we're making today. It's a cylinder with holes around the outside edge and it bolts onto the cubes that we made last week to extend them. And there's a deep blind hole down the center. And this is all aluminum once again. We'll start with this very nice piece of 6061 round bar and we'll cut some chunks here to length. And into the lathe we go. The majority of this part can be made with one setup, so that'll be very convenient. And I'm going to make sure that I've got room here for my parting blade. And then we will face off the end as is tradition. I'm using a high-speed steel tool here with a grind for aluminum, so it's got a very dramatic top rake on it, as you can see there. And then I'll square it up for the next operation, just using the end of the work, which is now faced and thus square. I put a witness mark past a little bit where the end of my part is going to go, and now we can start turning down to diameter. I'm using WD-40 here as a cutting lubricant, since this is aluminum. And as always with aluminum on the lathe, chip control is a little challenging. But we are doing okay here. And with that cleanup pass done, we can check and see how far we have to go. And of course, this is a metric print that I'm working from, and this is an imperial micrometer because it's what I have. So you got to be careful when doing this that you convert the tolerances as well and stay within the metric tolerances with your imperial measuring instruments. Now we are at diameter. That surface finish closely approximates poop, but that's okay. We can tidy that up later. As long as the dimension is good, then we can proceed. The first feature I'm going to make is this tiny little shoulder here. This registers on the opening in the end of the cube. And so to do that, I need to set up my tool at the very end of the part, but I don't want to do a cut, so I'm using a piece of paper here to feel the edge of the tool, and then I go 4th out in to get to the end of the part. And then I use a dial indicator on the carriage to get to the end position where I want my shoulder to be. And then I reset my indicator with a preload and zero it out once again. And then I can just turn down to the 0 on that indicator and I'll have my shoulder precisely dimensioned. Now with a shallow shoulder like this on a large diameter part, it's always kind of a question, should I do a whole bunch of little turning passes or should I do facing passes? I tend to end up doing a lot of little turning passes like this, and I'm not going to claim this is the most efficient way to do this, but this just suits the way my head works better and I have better success hitting the dimension if I do it this way. And we should be close, so I'm going to deburr that tiny little shoulder very carefully here with a file so that I can measure it without being influenced by a burr that might be on there. And unfortunately my micrometer will not fit in there, so I'm going to have to use the approximators. And luckily this is a pretty easy surface to measure, so this should be fairly accurate. And we got a little bit further to go, so I'm going to go in here and do my finishing pass. I'm using a 55-degree ground tool here that'll let me get in real close and do a nice shoulder there. And we do our facing pass out, turning all the way into the 0 on our indicator, clean up that face. That should be on dimension, and we have a nice finish on all surfaces. So, looking really good. And then I'll come back in here with a chamfering tool and touch up those edges. One edge I just need to break, and the drawing calls for a fairly generous edge on the relief area there. Next we're going to make the large blind hole down the center, and we're going to have to bore that, but I'm going to start by drilling it out as close as I can to final dimension. So we'll put a little center in there, and then I'm going to start with a 1/4 inch drill and work my way up in a few stages there. And so I'm just working the tailstock in. So after that 1/4 inch pilot, what size should I do next? I might typically go something like 3/8 as a nice next step up, but it's aluminum and it's almost lunchtime, so let's go for the 1/2 inch. And that was definitely the right call. Despite howling like a wounded banshee, it's cutting very, very well, and we're moving some material here finally. And then I went in with this 47/64 drill, which is extremely random, but it's the largest drill that I happen to own, and it is a little bit smaller than the final dimension that we need, so I decided to go in with this guy next. I have no idea why I own a 47/64 drill. I guess I needed it for something specific at some point, but I actually end up using it quite a bit because it's reduced shank and it's a good kind of maximum size for the small machine tools that I have. Okay, it's boring bar time, so in we go with my little boring bar here, and again using the paper trick to find the very edge of my shoulder there. There's one catch to boring a blind hole like this and starting with drills. You end up with a 118-degree cone in the bottom, which may leave too much material around where the boring bar needs to flatten out the bottom of the hole. So one trick to fix that is to go in with an end mill and create a flat spot on the bottom of your hole at the exact right depth. So to do that, I'm going to use a Morse Taper 2 end mill holder in my tailstock. However, if you do this, make sure to put a piece of threaded rod in the end of the holder, otherwise you won't be able to eject it with the tailstock. The reason is that a Morse Taper 2 end mill holder like this is designed to go in a Morse Taper 2 mill, which is going to have a drawbar that threads in the back. And so the shank on that end mill holder is too short for the tailstock to eject. But you can see here what a nice flat spot that made in the bottom of the hole for us, and that was a 2-flute center cutting end mill that I used there. And so now I can touch off with my boring bar and start working our way in. And when it comes time to face the bottom of this hole, that flat spot that we made with the end mill gives us a nice big target to hit, so we can go into depth and face our way out and end up with a nice surface finish and a perfectly flat bottom at exactly the right depth. We should be close to final dimension now, so I'm checking it with my telescoping bore gauge, figuring out what I need for the final pass. Now as I do this finishing pass, you might be thinking, you know, that shoulder area there is getting pretty thin. Is that right? To that I would say, well, where the heck were you 4 weeks ago when I was making this part? Yeah, that's not right. The bore is the correct diameter, but that outer shoulder is not. But I decided to clean out this hole, check my final depth, and when using a Q-tip to clean out a bore, make sure you don't go into the ear canal. That's really important. And then we'll get our depth gauge in there, and things are looking really good. I got my depth right on. I'm really happy, but yeah, this is around the time I noticed how thin that shoulder became, so that was clearly not right. I confused this shoulder diameter with the smaller one on the other end. Now luckily, because of the setup we've used here, we have not scrapped this part. I can come back in and reface the end of it and reform that shoulder and then just deepen the bore a little bit. We're back in business. Bob's your uncle. Customers none the wiser. Well, unless they watch YouTube, which I guess he does because, you know, David's actually in this video. But the point is, it doesn't matter because he got the part and we didn't actually lose any material, and in fact this didn't even cost us that much time. So mistakes are not always fatal in machining, even though it can feel that way when you've got hours and hours invested in a part. And now you can see that shoulder is definitely the correct size. Things are looking much, much better now. Now let's come back to that poopy surface finish and clean that up. Luckily aluminum is very easy to improve the finish on with a little bit of red Scotch-Brite on there. As we say in the race car business, regardless of the extent of the damage, that'll buff out. Okay, we need to square up the tool post again, so this time we'll do it with the tailstock quill, which is another handy way to do it. Setting up to part off now. This is a pretty big part, and so my parting blade is not going to reach, so I need to extend this guy. I keep it as short as I can for maximum rigidity, but of course the standard holders for these things are angled, and so if you change the stick out on that blade, you also have to readjust the height of it so that it's on center. To align the blade with the relief area on the outer surface, I'm using a 1-2-3 block, and you just bring it in very slowly and watch that the blade isn't deflecting. And then I use an indicator to move the blade down the length that I need for my part. Now the part is longer than the 1-inch travel that I have on this indicator, so I'm moving it down 900 thou, and then I reset the indicator, preload it, set a 0 again, and then resume to get the rest of my length, plus, you know, some amount to face off the backside after I part this guy off. And some WD-40 for lubricant, lock everything down, get it nice and rigid, and away we go. Check out my parting video for all the deep dark secrets of successful parting, especially on small hobby lathes like this. Yes, you too can part on your lathe. And Yahtzee. Remember, we need 2 of these extensions, and I brought them both to that same point, and then I'm setting up for the second operation on the 2 parts. So we've switched out to the 4-jaw chuck, and I got my copper soft jaws on there, and we're going to set this guy up and get ready to face it off. And that backside is machined, and the relief fits inside the bore on the chuck, which is great because it means I can snug it up to the machined surface on the chuck, which is going to come in very handy later, as you will see. And then I get this guy dialed in. Start by just doing a cleanup pass on this face to get it nice and machined so that we can start taking some measurements. Looking good. Now we need to establish the length of the part, which can be tricky for something held in a chuck like this, but because the part is snugged up to the machined face of the chuck, I can use a depth micrometer to see what the length of our part is, and then dial in the remainder that we need to get it down to length. And I'm using the power cross feed there, which this lathe has. It's an unusual feature on hobby lathes, but if you can get it, it's very nice for situations like this. And then we'll switch out to my 55-degree tool once again, and I need to get aligned on that face, but I don't want to take another cut, so I'm using my machinist scale, which is a precision piece of stainless steel that's exactly 15 thou thick. And I use that as a feeler gauge, and then I set my indicator to -15 thou, and then I can dial in the depth of cut, and I know I'm going to land on the right place. This is a very similar operation to what we did on the other end, except this is a smaller diameter. This is the end that goes into the robot arm. So once again, I'm deburring before I take my final measurements to make sure that I'm not reading any kind of burr or other debris on the surface there. And then I do my facing pass, once again pushing all the way in, and then I lock the carriage and wind out the cross slide to face off both surfaces on dimension and with a nice finish. And then just a little kiss with the chamfer tool to make them all look nice and machined. And there's our first part, looking pretty sharp. We're done with the lathe work on these parts now, so it's over to the mill to drill some holes. And we need 8 precisely dimensioned 5mm holes, the length of this part. So I'm setting it up with a V-block and some thin parallels in the vise here. Tap, tap, tap that guy in and make sure everything's seated properly. And then I'll just do a little sanity check here with the half thou indicator to make sure that we are vertical. We certainly should be because everything's machined and everything's being properly constrained here, but just in case, I don't want to make a mistake at this point because these are very long holes. Any small error here would get quite magnified by the time you got to the other end of the part. And the whole pattern is a bolt circle centered on the center axis of the part, and so I'm going to use the coaxial indicator here to get that bore that we made aligned with the spindle of the mill. So I'm going to start by turning it by hand, and then once I get it in closer, I start turning up the speed. I start running it under power. I find that the closer you are to getting dialed in, the easier it is if the mill's running faster, and vice versa. And then I'm going to dial in my 8-hole pattern here using the bolt circle tool. And I showed this tool in detail in the last video, so watch part 1 if you want to know more about this. And then as an extra sanity check, I like to just make a little mark by hand with a center drill, and then you can use a caliper to measure from that divot to the edge of the part and just make sure that's landing where you expect according to the print. Now is the time to find out if you've done something wrong with, the coaxial indicator or with the bolt pattern that you typed into the DRO or something like that. Find out now before you start making 8 holes. Now, my V-block is a little bit too tall, but I was able to just get in there with a number 3 center drill, which is larger than I would normally use for this, but it gave me the extra reach that I needed to get in past that V-block. As they say in machining, clearance is clearance, but that doesn't mean it isn't butt clenching sometimes. Okay, so far so good. We see our bolt pattern emerging there. It's looking nice and spacey and mechanical. So now I'm going to go up to a 4.5mm drill because we're going to be reaming to 5mm, and I'm using WD-40 as a lubricant. And I ran out of the liquid stuff, so I'm using the aerosol version, which is pretty annoying, but it still works. Now, if you're really paying attention, you might notice a flaw in my setup. And if so, well, you're smarter than I was in this moment. I thought I was being pretty clever with this setup. And you'll see why here in a moment. Watch for it. Wait for it. There it is. Did you see that? That was me nicking the parallel with my drill. So why did that happen? So what I had done was I measured the thickness of this parallel, and I made sure that it was thinner than the distance between the outer edge of the hole and the edge of the part. So it should have cleared it, but it didn't. What I didn't account for is the presence of the V-block. The V-block, of course, is setting that parallel quite a bit inboard from the outer edge of the cylinder, and so it was actually ended up aligned with 2 of the 4 holes in the top half of the cylinder. So what I did was I did the rest of the holes because I had this nice setup, everything was dialed in, I didn't want to disrupt it. So I did the other 6 holes that were clear of the parallel. You can see on the movable jaw the parallel landed where I thought it would, and so it was clear of all of these holes. So I did the rest of the drilling and reaming operations, and then I would come back and figure out what to do with those other 2 holes later. So after a long stop and think, as my mom would say, I decided to put a strap clamp on this V-block just to make sure that it doesn't move after what we're about to do, because this is really what's referencing the part to everything else on the machine right now. So I want to make sure that doesn't move. And then I clear out all of the chips to make sure those don't interfere with what I'm about to attempt. And then I loosened the vise ever so slightly and just indexed this guy around by hand. I loosened the vise just enough that I could turn it. And then I line up one of the problematic holes with the 4.5mm drill that made that hole. And it's not going to be perfect because drills tend to cut a little bit oversized, but it's going to be very close. And then using the DRO, I moved to where the other hole is, and the drill should align the same way, and it did appear to do so. So it looked like I had it successfully rotated 180 degrees, and so then I just finished those holes and then reamed them both to size. And this actually worked really well. I could tell when it was time to ream, I could tell that the reamer was cutting the same amount around each of the holes, which means that I had succeeded in positioning the holes 180 degrees from where they were when the first drill had gone down. Okay, we're done with that setup. Let's take a closer look at my shame there. You can see where I nicked it with the drill. That's quite disappointing, but I'll stone that out, and this parallel will still be usable as long as I avoid that area of it. But so far so good. That part is looking pretty decent. So we'll do the other one the same way. And now we're on to some cleaning and some deburring. So I'm using a basic Noga tool here to deburr those small holes all the way around. And I'm quite pleased with how that turned out. It looks very spacey and machine-like. Quite pleased with that. Let's take a look at how it interfaces with the cubes that we made last week. So you can see those 2 surfaces register together, and that fits in together very nicely like adult Lego. And those bolt holes all line up around the outside, so that's also good. I'll leave you with one last pro tip. Remember, we needed 2 of each of these parts, which is 4 parts, but it's actually easier to make the parts once and duplicate yourself, because then that's just 1 duplication operation to get 4 parts instead of duplicating each of the parts, which is 2 duplication operations. So think about that next time you're planning your setups and your order of operations. Duplicate yourself first, and the job will be a lot easier. All right, let's go back to David and see how these parts are actually used on the robot.
Hello, Quinn. This is Dave again from Dragonfly Engineering. So I got your robot end effector parts in the mail the other day, and they look really great. I think these are going to be perfect for the robot, so they don't keep whacking their wrists from the shorter one. So this extension is key. So let's go ahead and load this guy onto the white robot. This robot I'm bringing up into production now, so this is perfect timing. This portion goes right on the end of the arm here. There's a bunch of M5 screws and a dowel pin. I don't have the M5 dowel pin because of shipping restrictions currently, but yeah, so the tip fits onto the end of the cube here, which is a universal mounting cube. And then all of this fits onto the robot. And then we got some of our M5 screws here. So let's go ahead and string this guy on. So now that this end effector is on here, the robot can now move in full motion, which is kind of nice. See how it no longer whacks its wrist and pretty decent rotation as well. We designed this end effector universal mounting cube for the robot to mount these magnetic bases, these kinematic bases. And they basically consist of 3 ball bearings and 3 sets of V-groove made out of cylinders and a bunch of strong magnets. So basically they're designed just to pop onto the end of the robot. And then if you want to quickly switch out your setup, you can pull one off and then you can put a different one on, like so. The other nice thing is if you've got your claw on here and you screwed up your program and you crash the end of your robot, then there's a better chance that this will just kind of knock off and not do much damage or jam up your robot. Everyone's good here, so the team will use the other ones that you've made and we'll get to work.
Okay, job done. Back to Imperial. Yay! All right, thanks David for sending this project my way. This was a lot of fun. I love robots. I love aluminum. I like making machine parts, so this was great fun. And do check out David's channel, Dragonfly Engineering. He's got plastic injection molding machines and robots and lots of cool stuff. Thank you very much for watching. If you can swing it, throw me a few bucks on Patreon. I'd love it. I'll see you next time.